Hey everyone, and welcome. Today, we're diving into a new idea that is, well, it's truly radical. It's a theory that suggests everything we know, from the tiniest particle to the biggest galaxy, might all come from one single hidden source.
So, let's just kick things off with a pretty bold question. Our current theories in physics, they're unbelievably successful. But what if, for all their power, they're actually fundamentally broken? What if they have these deep, unfixable cracks running right through their foundation?
And those cracks are what lead us to some of the biggest unsolved mysteries in all of science. You see, modern physics is kind of built on two giant pillars. They both work fantastically well on their own, but, and this is a big but, when you try to get them to work together, they clash. Big time.
On one side, you've got Einstein's masterpiece, general relativity. That's our rulebook for the huge stuff, planets, galaxies, the whole curve of space-time. It sees space-time as this active geometric stage. But then, on the other side, you have quantum mechanics, the beautifully weird rulebook for the tiny world of atoms and particles. And here's the kicker. Quantum mechanics just assumes that stage, space-time, is totally fixed and passive. They just can't both be right, and this conflict is a massive roadblock on the way to a true theory of everything.
This fundamental disagreement leaves us with some absolutely tantalizing, head-scratching puzzles, like why does just looking at a quantum particle seem to force it to pick a reality? Why on earth do neutrons seem to live longer when they're flying free compared to when they're stuck in a bottle? And get this, why do the masses of certain particles follow a formula that is so bizarrely perfect it feels like some kind of cosmic cheat code? Our best theories just don't have good answers.
So, what if the problem isn't with the theories themselves, but with a basic assumption that both of them make? What if empty space isn't actually empty? This leads us to a fascinating new idea, the living vacuum theory.
The official name is Dynamic Vacuum Field Theory, or DVFT for short, and its core claim is going to kind of blow your mind. It says that everything, space-time, matter, you, me, we're not just in the universe, we are the universe. We're all just different kinds of vibrations and knots in one single underlying physical field that we call the vacuum.
Okay, let's unpack that, because it's a huge idea. Imagine this vacuum field is like a giant cosmic drumskin stretched across all of reality. It has an amplitude, that's kind of like the tension in the drumskin. Any bumps or dips in that tension are what we feel as mass and gravity. But it also has a phase, which is like the vibration of the drumskin. And those vibrations, well, that's what we experience as all the weirdness of quantum mechanics and the other forces of nature.
Now look, a bold new theory is one thing. But can it actually do anything? Can it solve problems that have stumped physicists for decades? Well, this is where things get really, really interesting. Let's take a look at how this idea of a living vacuum gives us some surprisingly physical answers to those mysteries we talked about.
First up, the strange case of the disappearing neutrons. For years, scientists have been trying to pin down exactly how long a neutron lives before it decays. When they measure a beam of them flying free, they get a lifetime of about 888 seconds. Simple enough? But when they trap the neutrons in a physical bottle and measure them, they decay faster. They only live for about 879 seconds.
That's a 9-second difference. Now you might be thinking, 9 seconds, so what? But trust me, in the world of particle physics, that's not a small error. That is a massive, glaring gap that has had scientists scratching their heads for years. Our current rule book says a neutron is a neutron, period. Its lifetime shouldn't change.
So, what's DFFT's explanation? It's actually pretty elegant. It says the neutron isn't changing at all. The vacuum is. The physical walls of that bottle ever so slightly change the properties of the vacuum field inside it. This tiny change actually lowers the energy barrier for the neutron to decay, which makes it happen faster. So it's not some strange magic, it's a physical mechanism. The environment itself is part of the experiment.
All right, let's tackle the next puzzle. This is one you've probably wondered about yourself. We all hear that the quantum world is just bizarre. Particles can be in lots of places at once in what's called a superposition. So why don't we ever see that in our world? Why isn't your cat napping on the couch and chasing a laser pointer in the kitchen at the exact same time?
So standard quantum theory doesn't really have a built-in size limit for this stuff, but experimenters have been pushing to see how big they can go. Right now, the largest object ever put into a true quantum superposition has a mass of about 10 million atomic mass units, which is incredible. But this is where DVFT makes a real testable prediction. It actually calculates that there should be a fundamental upper limit, and it puts it right around 50 million AMU, which is shockingly close to where our experiments are already getting.
And the crucial point here is that DVFT gives us a physical reason for this limit. See, a really massive object trying to be in two places at once creates this huge strain on the phase of the vacuum field. At a certain point, that strain just becomes too much. The vacuum itself can't handle it, and it basically forces the object to pick one location. The quantum weirdness collapses because the vacuum says it has to.
And finally, we have one of the strangest magic numbers in all of physics, the Koide formula. It's this wild equation that connects the masses of three related particles, the electron, the muon, and the tau. When you plug their measured masses into this thing, the answer comes out to be exactly 2/3. I mean, with stunning precision. In the standard model, this is treated as a complete and utter fluke. There's just no reason for it to be true.
The explanation from DVFT is just beautiful. It suggests that these three particles aren't random at all. They represent the only three stable ways the vacuum field can be arranged in this particular way. They are geometrically locked into place, exactly 120 degrees apart from each other, like three perfectly balanced points on a circle. And that physical geometric setup forces their masses to obey that strange formula. It's not a coincidence. It's a direct consequence of the vacuum's own structure.
So let's just zoom out for a second. What does all of this really mean? Well, if this theory turns out to be right, it's not just some small update. It's a completely new map of reality. One where the vacuum isn't just a passive stage that the play of the universe happens on, it's the main actor.
This is a pretty fundamental shift in how we look at everything. Where the standard view sees an empty, boring stage, DFT sees an active physical field. Where the standard model has all these weird numbers and rules that we just have to accept, DFT suggests they actually emerge naturally from the vacuum's own geometry. It's trying to replace mathematical puzzles with physical mechanisms, and it could, potentially, finally unite our two great conflicting theories of reality.
Now, we have to be really clear here. Dynamic vacuum field theory is a new idea. It's speculative. It has to earn its place at the table. The good news is it makes specific testable predictions about that maximum size for quantum objects, about how particles decay in different environments. These are things scientists can actually go out and test in labs over the next few years. Science is going to put this theory on trial.
And that leaves us with one last, really fascinating thought to chew on. For centuries, we've looked for answers way out in the distant stars and deep inside the tiniest atoms. But what if the deepest secrets of reality have been hiding in plain sight this whole time, in the very nothingness we've always called empty space?